Thank you everyone for remaining for my talk. Thank you to all the speakers. Thank you to the organizers. I was actually upgraded to an invited talk because I was the only contributed talk, so they just added me in, which I certainly appreciate, because then I get to put that on my faculty activity report. Okay, okay, so I'm going to be speaking on a closure theorem, which means I'll be saying what a closure is, for graph tenacity, and I'll be defining what tenacity is. So this talk is primarily a nice result that comes about with a little bit of intuition and a little bit of algebra, which I like. So I'm going to define the k-stability of a graph property, then related to that, the k-closure of a graph, and then I'm going to define the tenacity parameter itself, and then provide the, and this is what I like, best possible k-value for k-stability of tenacity. So this k-value will be a lower bound, and it will be demonstrated that that lower bound cannot be reduced and made weaker without losing the implication of the theorem. Okay, so I always enjoy this when I get a result that involves an inequality with a fixed lower bound. I like to explore, well, can I demonstrate that that lower bound cannot be improved upon? And it just taps into that primal urge to have something that's best. So we're going to do that. So d of u refers to the degree of a vertex within a graph. P is a graph property when we say P, and we're going to have k as some positive integer. So in a paper, Method in Graph Theory, Bondi and Schwatel, they gave the following definition. A property P is said to be k-stable if whenever G plus a specific edge has the property P and the sum of the degrees is at least this k-value, then G itself has the property P. So we're going to be looking at certain properties for which adding an edge certainly preserves that property, so monotone increasing, but removing an edge wouldn't guarantee to preserve the property as well. But we have this additional condition on the sum of degrees for, in this case, U and V would be assumed non-adjacent in G. Okay, so here, a well-known result of OR implies that the property of containing a Hamiltonian cycle is n-stable, where n is the number of vertices. So if we take two non-adjacent vertices in G, and the degree sum is at least n, the number of vertices, then if we know that adding that edge would make the graph Hamiltonian, then the graph we have is in fact Hamiltonian. So this notion involves taking a degree sum of two non-adjacent vertices within a graph and looking at a lower bound. So when we have a fixed positive integer k, the k-closure of a graph, this c sub k of g, is obtained by you start with the graph G and you recursively add edges between non-adjacent vertices whose degree sum is at least k. So by the time you're done with this process, you have a graph for which the degree sum of two non-adjacent vertices is less than k, at most k minus 1. Because if it was k or more, you would add an edge. And it turns out that this closure is in fact unique with respect to k. So a proposition that follows is that if P is a k-stable property and the closure with respect to k has the property P, then G has the property P. Because once we have the closure, we can reverse that recursive process, and each time we take out an edge, we have those edges joined in such a way that they satisfy the k-stability notion. So then removing the edge preserves the property, removing the next edge, and down until you recover the original graph G. Okay? So that means that G is Hamiltonian if and only if its closure with respect to the number of vertices is Hamiltonian. Okay? This is an if and only if statement because clearly if it's Hamiltonian, adding the edges to achieve the closure, it'll be Hamiltonian, but vice versa as well. Okay? So here's a 6 closure of a given graph. So note 6 is the number of vertices within the graph itself, and I've labeled the degrees in red. So what we're going to do is we're going to systematically find any pairs of non-adjacent vertices with degree sum at least 6. In this case, we have these UV where the degree sum is 6. So we'll join them. Now we can pick another pair recursively. UV, the degree sum is 6, so we'll join them. And the degrees change as we add edges. And then here we have 4 and 2 between this U and this V. So that's our 6 closure, because if you look at any pair of non-adjacent vertices, the degree sum is at most 5. Okay, this one down to this one. These two would have a degree sum of 5. Those two would have a degree sum of 4. So that's the 6th closure. And more importantly, because we were looking at 6, which is the number of vertices, and we started off with a non-Hamiltonian graph, the closure is in fact non-Hamiltonian as well. Okay? So that's the notion of K-stability and a K-closure and how we can translate that into these closure theorems. One thing I should mention is that oftentimes the notion of a closure is used to prove, let's say, that a graph is Hamiltonian under some conditions, and then what we do is we assume it's not Hamiltonian and use the closure, because the closure will be non-Hamiltonian, and then you have this degree sum of non-adjacent vertices less than n as part of one of your tools that might help you along in the proof. Okay, so I decided, well, let me look at another graph property, and this one is tenacity. And this one is also monotone increasing. Adding edges preserves it. So tenacity, it's a vulnerability parameter that was introduced by these individuals in 1994. It looks at graph removal and then how badly damaged the graph becomes in terms of how many components there are, and also the order of a largest component. So what's the biggest connected group of individuals that can still reach communication with one another? And then this is similar to the toughness of a graph, and we'll see that the definition, the formal definition for tenacity is we look at all ratios formed by taking vertex cut sets. So we take vertex cut sets, take the order of the cut set plus the order of a maximum component within the G-s subgraph, divided by the number of resulting components in G-s, in those induced G-s subgraphs. Take all possible cut sets, look at the ratios, and pick the smallest one. If anyone here is familiar with toughness, we just remove that largest component value here, the order of a largest component, and you just take order of the cut set over number of components minimum, and that's the toughness. We actually define, for the work that I do, I find it easy. Many of the results that follow can be transferred to include the complete graph if I take the tenacity to be n itself. Okay, here's an example of a graph with tenacity 2. I'm not going to show all the cut sets, but the cut set that does get us the minimum is take the bottom 2 vertices down here, and then we have a component of largest order 2 and 2 components, so 2 plus 2 over 2. Okay, so in fact, the theorem that I'm going to present for stability is with respect to tenacity, but lower bound on the tenacity. So we say a graph is t-tenacious if its tenacity is at least t, just like we say a graph is t-tough if its toughness is at least t. So here's the value I found for t-tenacious. So the property of being t-tenacious is this ceiling value, where t is the prescribed lower bound on the tenacity, and n is the number of vertices within the graph. So this is a ceiling, so it's the smallest integer greater than. Moreover, this is the best possible value for which t-tenacious is k-stable. If we reduce that number by even 1, having that as a lower bound would not necessarily guarantee the t-tenacity. Okay? Yeah, so this means that if the graph with the edge UV is t-tenacious, and then the degree sum is at least that prescribed value, then the graph itself is t-tenacious. Okay, so here's the proof. We're going to do it by contrapositive. So G is a graph on n vertices. We're going to take two non-adjacent vertices. And what we're going to look at is we're going to assume that adding the edge is t-tenacious, but the graph itself is not. And we're going to show that we end up with the reversal of the inequality. Okay? So as a result, with the inequality in place, G itself would have to be t-tenacious. So we take a set which generates the tenacity, a cut set X which gives us that minimum. Now, it turns out that if either U or V were in X, so here's X down here, and what we have is we have some components up top. And we have some edges going back and forth between X and the components. Now, if U and V are non-adjacent and one of them happens to live down here and the other one lives up here, for example, or they both live in X, well, the result of removing X from G plus UV would remove the edge we just added, UV. And then we would get the same thing as the graph originally minus X, because we would lose the edge UV that we just put in. So it turns out that we would end up saying that the tenacity adding the edge, well, it didn't go up. So in this case, we know that the tenacity is of adding an edge could either go up or stay the same. So it must have stayed the same, but then by assumption, our graph has tenacity less than t, but we're assuming that adding the edge makes it greater than. So U and V, neither of them can live in the set X, the cut set. So we have to assume then that U and V both live up inside either in the same component or different components, but outside of X, the complement of X. So we're going to call X, lowercase x, the order of that cut set, and then omega is the number of components. And then these components are labeled h1 through h omega, but more importantly, actually, I want to refer to these as numbered and labeled h1 up until h omega, where h1 is a component of largest size, order, largest order. So this one has the largest order of all components, or there might be some that hit that order as well. So because we know that U and V cannot live in X, they might be in the same component, they might be in different components, but regardless, the adjacencies are at most within their component and then to X, which means that the largest degree of either one is all of the X. Within the component, there's at most the largest h1, and then if they're adjacent to everything in there, it's h1 minus 1. So both of them have largest degree x plus h1 minus 1. And then the rest here is algebra. Okay, so with this in mind, since we assume the tenacity of G, which is the x plus h1 over omega, is less than t, then we're going to use the fact that x is less than t omega minus h1. So here we go. Okay, each of these degrees is at most x plus h1 minus 1, so the sum is at most 2 times that. This is very advanced. I understand if you need to ask questions about this. I multiplied by 1, which is a very interesting feature of analysis. You just find the right one to multiply by. Okay, so t plus 1 down here. You may recall or not, but there's a t plus 1 in the denominator of that bound that I'm proving. So here, this is just distribution of this 3 terms through into the binomial here, t plus 1. Then I'm just regrouping things. Okay, so here, actually I didn't regroup. I used the inequality on x right there. Now I'm doing some regrouping. So here's a tx, h1 cancel out. I'm going to take the here t omega and negative t and group them into t times omega minus 1. This extra 1 here. Now the thing is, omega minus 1 may seem odd. Why am I representing it as a sum of 1s from 2 to omega? Well, that's the same thing, because I'm adding 1 omega minus 1 times. But here's the interesting part. Well, every single component has order at least 1. So if I replace that 1 with h minus 1, I might go up. Well, I'm sorry, hi, for I going from 2 to omega. Might go up. Now, I've got an h1 here and a coefficient of t in both instances and a coefficient of t here. But what is x plus the order of every component? It's the number of vertices. So that's the n appearing there. And then we get that the degree sum is less than that value. So if we assume that the graph was not t-tenacious, but adding the edge is, then the degree sum is less than this value. So if adding the edge makes it t-tenacious and the degree sum is at least this integer, then G must be t-tenacious as well. Okay? So stability is proven, and here's the best possible result. I'm going to prove that for an infinite family of t values, each one has an infinite family of graphs for which if we nudge that ceiling down by 1, these degrees, there'll be non-adjacent vertices, in fact all of them, will have degree sum equal to this minus 1. And adding the edge will make it t-tenacious, but the graph itself is not. Okay? So for some m, this is a different m than the order of a largest component. But I'm just saying, take the following graphs constructed in this manner. We're going to take a complete graph on m minus 1 vertices down here. This plus is my notation. I was raised by Douglas Bauer to use plus for complete join. All edges going from down here up to here. Now up here we have an independent set. Okay, just some independent vertices, complete join to this clique. Okay, so m is fixed, and we're going to create G sub m. Now, n is equal to, we just take the sum of all the vertices, so the sum of the two subscripts here. And then that can be arranged algebraically, and then it's possible to show that this ratio, which is inside the parentheses, can be simplified to 2m minus 1 over 2. Okay, so we're going to use that fact. So for any pair of non-adjacent UV, they have to be in this set of independent vertices. So the largest degree, they have actually degree equal to m minus 1 each. So if you add them up, you get 2 times m minus 1. Rearrange that. And then 2m minus 1 is an integer, so the ceiling of that is the same thing. And then if I double and divide by 2, it's the same thing. So now I've got the degree sum equals 1 less than my prescribed lower bound. So here's Gm. The degree sum of any two non-adjacent is 1 less than that lower bound. If we look at the tenacity, it turns out that we would get the tenacity by taking out these m minus 1s. Component order 1, so plus 1. And then the number of components is, well, this number of independent vertices. That can be shown, it's less than if we just didn't have this L here. And then that's our t value, because we would have m dividing away m. Okay, so this is not t-tenacious. But if we add an edge between any pair and create a component of size 2 up here, I'm sorry, order 2, I have to be careful with that. So then we get a K2 and then our isolated or independent vertices. But now calculate the corresponding tenacity, And again, we remove m minus 1. Largest component order is 2. And then the number of components goes down by 1. Okay? So instead of having that many components, I have that minus 1. Now that's greater than if we doubled the L in the denominator. Now we have a 2L minus 1 to factor out, m plus 1, m plus 1. So adding the edge does make it t-tenacious. So we've in fact demonstrated that if we bump that lower bound down by 1, that there are counterexamples where adding the edge will produce a t-tenacious graph, but the graph we have is not t-tenacious. Okay? So, yeah, that's just the theorem stated again. Or got my best possible. And then stated in terms of closures, G is t-tenacious if and only if its k closure is t-tenacious with the prescribed k value. Okay? So, I would be remiss. I am hosting a session 2 weeks from tomorrow in honor of our good friend and colleague Charlie Suffel, aka Pop. Or I guess for me, Pop Pop, because he's my academic grandfather. And yeah, so it's the AMS spring sectional meeting. It's up at Hunter College. It's Sunday, 9 to 5, and here's a list of speakers. Some individuals you've actually seen today, still here today. We've got a nice lineup in honor of Charlie. So if you have a chance, please come out and join us. If you're going to be at the conference, stop in and say hi. And
what's the title of the session?
Oh, the title of the session is, if you look it up, it's going to say Applications of Network Analysis in honor of Charlie Suffel's 75th birthday. Yeah. Yeah, so right in the title, it says, right in the title of the session, it says in honor of Charlie Suffel's 75th birthday. Yeah.
You can't lie anymore.
So what part of the day is it?
Oh, it's 9 to 5. So it starts at 9, 4 talks, then the lunch break, and then I think it's 5 or 6 more talks. I guess it would be 6 talks because there are 10 speakers. Okay? And thank you.
Questions?
Yeah. Okay.
Comment about that special session. This just goes to show you that they don't pay attention. You say, don't do this, please.
I'll tell you one thing. I had it in mind, but it was reinforced when John, well, he's not here right now, but I was pointing to where John's ghost is now. But yeah, John suggested it, and I ran with it. But we're more than happy to do it. Okay. And how did I do? Oh, look at that. Well in time for our dinner.
Thank you.
Okay. Thank you.